All right, so let's get started, folks. Um, give me a moment. I'll share my screen. Yep. Can you see my screen? All right. So in our previous session, we were discussing about how we go about creating the cost function. Okay. But before we went to the cost function, we started with this expression y hat to the power of y minus, I'm sorry, into 1 minus y hat whole to the power of 1 minus y. And the intuition was simple. The objective of logistic regression is to get a set of weights such a way that the y hat, which is an estimate of the probability that it belongs to the positive class, is very close to the value of y in the training data set. All right. So which means, for example, in this case, if you look at row number 1, y hat is 0.9, y is 1. So it's very close. Likewise, if you look at the second row, y hat is 0.2 and y is 1, far apart. The third case, y is equal to 0, y hat is 0.9, again far apart. The fourth case, y is equal to 0, y hat is equal to 0.1, so it's close. So the objective of this expression is to help us get to a number such that when y hat and y are close, you get a large value. And when y hat and y are far apart, you get a smaller value. Okay, that's the objective of this expression. And you can see that evidently here, where when y hat and y are close. So when I say close, I mean close from both perspectives, in the sense that you could have y equal to 1 and y hat can be close to 1. Alternatively, you can have y is equal to 0 and y hat can be close to 0 too. Even that's close, right? So whenever y and y hat are close, you would find that this whole expression, y hat to the power of y into 1 minus y hat to the power of 1 minus y, is pretty high, right? Now, what we also said was we would want to maximize this expression. I'll come to that in a moment, but before that, let's some food for thought, okay? I want you to think about it. I'm going to give 3 cases. So in all these 3 cases, there are 4 records. Okay, so which means 4 x vectors. Okay, imagine 4 x vectors, 4 records. You have the y value. Here's the y value. Here is y hat. So how do we figure out y hat? You take x, you calculate wx plus b, the dot product of w and x plus b. Put that into the sigmoid function. You get to y hat, right? Now what I've done here is I've taken 3 cases. Here is one set of weight vectors, another set, and then the third set. All right. Now, can somebody tell me before we proceed, how many features are there? Just look at this and tell me how many features are there. Sorry?
4 features.
Exactly. How did you figure out that it's 4 features?
Since it has 4 weights, 4,
Exactly. Correct.
yeah.
Right? So you can have 15 records, but still you'll have 4 features. Why do we have 4 features? Because there are 4 weights, W1, W2, W3 and W4, right? So going back to this expression, it's W dot X. So which means you take the weight vector and the feature vector, and then you take a dot product of the two, right? So that's fine. Now the question is, given this information that you have, which set of weight vectors would you choose? Forget the cross entropy and all that, okay? I'm not even, I don't even want to bring such terms here. But the question is, which set of weight vectors would you choose? Would you choose weight vectors 1, weight vector, I'm sorry, weights vector 2 or 3? Which one? And how do you go about doing it?
I would choose weight vector 3.
Okay, what's the logic?
All the values are close to 1.
Weights vector 3. Why not weight vector 1? There has to be a mathematics behind it, right? It can't be just intuition. There's a math behind it, folks. The question is, what is that mathematics?
Summation.
So who said summation?
It's me, Abhinav.
Okay,
Actually,
so when you say summation, what are you going to sum?
okay, summation of the y to the power y hat power y into 1 minus y hat power 1
Okay,
minus
why
y.
summation?
The values.
Why summation?
Okay, okay, let me put it this way, because while adding, we get the overall weights, overall value of the. Okay, let me average. Let us take an average.
Think and tell me. Think and tell me.
Okay, because when we are
Okay, let me
adding
put it this
data,
way. Let me put it this way. Okay, I'm going to rephrase this question in a way so that bells will start ringing in your brains. Okay, so let me rephrase this. I'm picking up 4 different. Okay, these are 4 different sets of X, right? I take a bunch of X here, calculate a Y hat. Of course, I have a Y. Then I pick another set of X. Look at it this way. It's like as though from the population of X's that I have a whole population of X1, X2, X3, and X4. I pick 4 out of them. Okay, I pick 4 values from them. Let's say I pick, so from an entire population of, so here is X1, X2, X3, and X4. Okay. Now these are basically, features. Now each of these features can take any value, correct? So think of these features as having, infinite set of values. Okay. What are we doing? The first case 1, or rather record 1, I'm picking 4 values out of them. Okay, some random 4 values, say 1, 2.3, 1.2, 5. Okay, and of course the y value is 1, and of course I have a y hat. Okay, then I have that whole probability. Next, I pick another record again from the population X1, X2, X3, and X4. Okay, so it's like as though I'm dipping into X1, X2, X3, X4 to pick 4 values. First question, the values that I pick here, is that dependent on values that I pick here that I'd already picked before? Is it
no,
dependent? No, it is not.
no.
Okay. So this could be something like a 2, 2.1. This could be 1.6, 7. Let's say this is, so what is y? Second row is 0. And then you have again some y hat. So let's say 0.9 here, 0.9 here. Sorry, not y hat. This is that whole, this whole thing. Okay, let me just copy that. All right. Likewise, record 3, record 4. So for each of these records, and I'm going to use a word that will ring bells, I can consider them as independent samples from a population, right? Why? Because it's like as though I'm dipping my hands into a box. One box comprising of x1, another box comprising of x2, third box comprising of x3, fourth box comprising of x4. I pick one data point from each of those boxes. That's record 1. Then I close my eyes. Then I again pick, again, it's like as though, think of that as an infinite box. I can keep picking, right? And we know that what I pick in record 2 is independent of what I had already picked in record 1. Very clear. Now I know the probability. This probability is 0.9. This probability is 0.9. The third one is 0.99. The fourth one is 0.99. Now what do I want? Given the W's, I want to ensure that when I pick all these 4 records, the occurrence of this probability is maximized. So what would I do? Forget the maximum thing first. Let's not even use the word maximum. We'll come to the maximum thing later, because that comes from optimization, right? I want to maximize it. So, and what I'm saying is I'm comparing this set with this set. So how do I do that comparison? What should I do? Should I add?
Okay, let me make it. Okay, you want this set of things to happen. So what is the probability for it to happen? You're asking that?
Yes, that's right. Correct.
Okay, we have to multiply. So
exactly. So which means the probability of all 4, the probability of me picking up these 4 x1, x2, x3, x4s, that combination, and given that y is 1, whatever values, is I just multiply these. All right. Because this probability is independent of this probability, is independent of this probability, is independent of this probability. So since they're independent, the probability of this occurring and this occurring and this occurring and this occurring is the product of all 4. Now, can somebody do this for the other set? Do you have Excel? Plug the numbers. So the second set is 0.92. So that was the first set. Second set.
It's 0.745.
Wait, 0.92, 0.92, 0.9, 0.99. Okay. What's wrong? Sorry. Is it 745 or 754?
It's 754, and for vector 3 it's 74.
Okay, let's do vector 3. 0.93, 0.92, 0.88, 0.99. So the product is 745. Okay. So what would I do? I would just make sure that I pick up the set of weights, the vector that maximizes this combined probability, right? So evidently, now tell me which set of vectors would I pick? Is it the first set, the second set, or the third set?
It's the second. It's first.
First set, right? Because the
It has the
probability
highest
of the four, I mean, if you have these four records, the probability of us getting all of these simultaneously is 0.793881, which is the maximum compared to the rest, right? Now, remember, folks, we have one problem with probabilities. It is always between 0 and 1. So here it is 4 records. Life is easy. What happens if it's 400 records? What will happen? We discussed this before. What would happen? If there are 400 records, what would happen? Let's say you use a computer to solve it. Let's say 4,000 records. Let's say 4,000 records or 40,000 records. What would happen in that case?
It's computationally expensive.
No. Is it computationally expensive? Is that the problem?
It will
The
exceed 1.
probability will reduce to 0.
Hard to multiply all.
Okay.
What problem would you face?
The probability will
Probability
reduce to
is
0.
very
We
low.
continuously multiply.
Correct. Yes, it will tend to 0, but what is that problem called? I mean, yes, it tends to 0, but why is that a problem?
It takes longer time for computation.
Is it so? Does it take longer time?
Yes.
Why? It's just a multiplication, right? Why should it take longer time? Would it take longer time if it's...
Because we arrive for all the records, it's 0. So we wouldn't end in an correct solution.
Say that again. Say that again.
Okay,
So
plus-
let's say instead of 0.9, this is 0.01. Okay. And then let's say something like this. Okay. So I multiplied product. This. Oh, goodness me. Why is it 0? Why?
10 power.
That even happening is very low and still.
But why is it 0? That's not 0, right?
It's going beyond the range of beyond some range of numbers.
Exactly. That's the
Some
problem.
decimal points.
So, the computer doesn't have the ability to store that many decimals, right? Typically. So that's the problem when you face when you're dealing with small numbers, essentially between 0 and 1. And if you multiply those small numbers across, say, 1,000 times, 10,000 times, you'll face that problem. So what is the way out?
Taking log.
Take
For
log.
them.
Exactly.
Scaling back.
Taking log.
Take the log.
Log and adding them together.
Exactly. So we are saying instead of multiplying, what we do is we take log of this, let's say to the base 10. Base doesn't matter. And then what do? Just sum it up. Right? Because we know that if you have an expression log of A, B, C, D is, what is it? Log A. Then what? Into log B?
Plus log B. Plus log.
All right. Plus log B plus log C plus log D. Sorry. All right. So now I have a question. Sorry. Let's do this. Now, don't you see that I could have done two things? I could have calculated this number, calculated the minimum, correct? I'm sorry, the maximum, or taken the log and then calculated the maximum. Both will give the same. Would you agree? Because our objective is just to maximize, correct? So I could have figured out the product, I could have maximized it, in which case I would get set 1. Alternatively, I could have taken the log, summed it up, I'll still get set 1. The third possibility is, since we are dealing with cost functions, what do? You change the sign and do you maximize or minimize if you flip the signs?
Minimize.
Minimize, exactly. So what you do is you put a minus sign. It's like saying, look, I'm calculating negative log. Sorry. All right. So which means let me put a minus sign here. And then do I maximize or minimize now? I minimize, right? So if you go back, we have done something similar here. So if this is for one data point, folks, okay? This is for one record. What you're seeing here is for one record. It's like saying, look, I'm calculating y hat to the power of y into 1 minus y hat whole to the power of 1 minus y, which is essentially, say, this number. Then I take the log, which is this number, and then I change the sign. Of course, I've changed the sign here. Instead, I could have changed it here itself. Correct? I could have done that. I could have done this and then just summed it up. I could have done this as well. Okay. So what you're seeing here, this is a cost function, or rather the cost. It's also a cost function. It's also a cost of just one record. All right. So if there are M records, how would the cost function look? Let's say there are M records.
Product of all those.
No, think. We've made it simple now. I've already converted it
Addition
into
of
log.
M records
Log of
first.
addition.
Exactly. So it will be, I just need to do a sigma, correct? Would you agree? X would change to xi, w to some wi kind of thing, or it's a vector. And I just do a summation, correct? Sigma. And then if I'm calculating an average cost function, okay, an average, then what do? After doing that sigma, I divide it by
Divided by the number of data points.
and I said there are M records. So how many? How I
M,
divided by
M, divided by M.
M, exactly. So if you have M records, the average cost function that you're going to minimize is sigma of this whole thing across records divided by the number of records, which is M. All right. So let's look at this. We'll come to that. We'll come to gradient descent, but forget the argmin, folks. Okay. Just look at this. What you see on top is the function for one record, the cost function for one record. So can somebody tell me what is sigma w dot x plus b in our representation? Is it y or y hat? Just to wake you up.
Y
Y
hat.
hat.
Correct. So this is like saying minus y log y hat plus 1 minus y log 1 minus y hat. Correct? It's just that instead of y hat, They've replaced that with this complex expression, sigma of w dot x plus b. Okay. All right. Now forget the arg min for a moment. Okay. What they've done is basically LCE is the whole function, folks. The cost function per record. Right? Or the cost per record. I don't want to use the word cost function here. Cost per record. Okay. Then if you look at it, this says I'm summing it up from I equal to 1 to I equal to M. Okay. So I'm summing up the cost across M records and I'm dividing it by M. So that gives me an average cost. Okay. I hope it's clear so far. Now, the question is, I have this average cost and I have to figure out a way to minimize this average cost. Right? Because that's the whole objective. If you think about it, what we we didn't do optimization here, but if you look at our objective, what were we trying to do? Okay, question. Was this the average cost or the total cost? Each of these numbers.
Total cost.
Total cost. So can somebody tell me if I have to calculate the average cost, how would I do it? I'll take this and then
Divided by 4.
divided by 4. That's right. Okay. Sorry. Of course, this changes nothing, right? Why? From an optimization perspective, you're dividing it with the same number 4, right? So this number, I mean, if this was the minimum cost, you'll continue to get the same thing. You're not going to get something dramatically different. But from a function perspective, when you're talking of average cost, you calculate the total cost and then divide it by the number of data points, which is 4 in this case. Okay. So going back to, sorry, let me go back to this. So the objective is to minimize this average cost. Figure out the weights such that this function, the average cost function, is minimized. That's the whole objective. Okay. Now, this is no different from what we did earlier, with linear regression. What were we doing there? We somehow figured out a cost function. Can somebody tell me what is the typical cost function of linear regression? So let's say,
Why?
I'll throw up something, okay, so let's say I have my hypothesis, which says W1x plus, say, B. Let's say that's the regression hypothesis. And then I have, say, okay, let me put it this way. I'll give some values here. X1, then X2, and let's say this value is Y1, Y2, X3, Y3. Now, can somebody tell me how would the average cost function look here? In the linear regression world, what is the average cost function here? So first things first, what are the variables in the cost function? Is X1, Y1 the variable or W1B the variable?
W1B.
That's right. Correct. It's always the weights and the bias that's the variable. You already know what is X1 and what is Y1, right? When you do linear regression. Correct. Now tell me, if I have 3 data points here, and if I'm figuring out the average cost function in the linear regression world, how will that cost function look like? You don't need to do that expansion, but just tell me how it will look like.
Summation of y1 minus
Go ahead.
w1 x1 b whole square
Okay.
plus y2
So
minus
so
w2
so
x2
what are we
plus
doing?
p.
This is the estimated, correct?
Okay.
This is the actual, correct? This is what the regression equation estimates. This is the actual. You figure out the difference. Y1 minus W1 X1 minus B, correct? And then you square that. You do something similar for this row and this row. And then what do you do after that? You take an average because you're
Yeah,
figuring out an
that's why
average
it's
cost.
called mean
It's
squared
called,
error.
exactly. That's why it's called mean squared error. So you divide it by 3, correct? Now, we are doing something similar here. Nothing has changed if you think about it, right? Here is a cost function. We have figured out the average cost. And we just have to figure out the values of, in this case, W and B, of course, such that the average cost is minimized. Okay. Now, in the linear regression world, as we discussed before, there is a closed form solution, which means you can use partial derivatives to figure out exactly. You can solve equations. So if you think about it, we could have calculated the derivative of this expression, equated that to 0, and then you will get an equation. Solve those equations, you'll get the value of W1 and in this case B. All right. But we also know that in many scenarios, you may not get a closed form solution. So that's called as a closed form solution, right? When you have an equation, a bunch of equations, and you solve for the equations to get the values of the variables, then that's called a closed form solution. Now, as I said, not in all cases, you will get a closed form solution. And that's why gradient descent comes into picture. So what do? We draw I shouldn't use the word draw. Draw is because when I say draw, you can draw something if you have two variables, but then the more variables you have, you'll struggle to draw it. Okay. But let's imagine you're able to draw something like, I'll probably show something from the book. Give me a moment. Are you able to see the book?
Yes, yes.
All right. Give me a moment. So let's go to logistic regression. By the way, much of my content is coming from this book. This is a wonderful book, folks. I'm loving it. There's a lot of stuff here related to NLP, but if you take the NLP stuff out, there's a lot of basic algorithm related stuff. And it's not mathematically too intense in terms of notation. Some of the books are very, very intense mathematically. You'll go crazy with the math. This is okay. It's manageable. So let's look at the function that I talked about. Okay, here we go. Something like, so this is like the cost function. This is one example where you have one W. Of course, in our case, there are many W's, W1, W2, W3, W4. But let's say there's just one W and then there's a B. Then you can draw a cost function and you can see that you can start from a point and eventually move to the bottom of that surface. Okay. And this process of moving from some point and going all the way down to the bottom of the surface is called, it's an optimization algorithm. Question, is gradient descent an ML? Is that a machine learning algorithm or an optimization algorithm?
Optimization algorithm.
Okay, be very
Optimal.
careful, okay? So never ever say that gradient descent is a ML algorithm. No, it isn't. It is an optimization algorithm. So given a function, gradient descent will allow you to figure out, I mean, it offers us a way to get to the minima. That's it. Okay. So it's an optimization algorithm. So coming back, so here we go. We got to figure out those W's, the W1, W2, W3s, and W4s of the world, and the B as well. So we have the cost function that we are going to minimize, the average cost function as we call it. And as I said, not all functions of the world have closed form solutions. So in which case, the way out is to use the gradient descent algorithm. Okay. So let's look at this. I'm going to read this for you. The goal is to figure out the optimal weights W and B. W is of course a vector, B is a scalar here. Okay. In the ML world, this is parameterized as theta. Okay. We're looking to find a set of weights which minimizes the loss function averaged over all examples. Now, can somebody tell me what does arg min theta means? What does that mean? What does this function mean? Arg min.
Tan inverse.
No, that's, come on, that's arc, man. ARC,
Okay.
arctan. This is
It
ARG.
passes,
Values.
it passes a set of theta values and it will return a minimum theta value.
Think. Does it return a minimum theta value?
No, the theta will pass to the function, the average function. It will minimize that value. The function.
Minimize which? Okay.
The 1 by m summation of
Okay.
the cost function.
So what? Correct me if I'm wrong. The way I'm
Yes.
interpreting what you're saying is the theta is okay. What it does is, if you look at this, theta can take a variety of values. Correct?
Yes, we see.
So this gives us the theta that minimizes the function.
Yeah, we see.
Correct? So it's not very complex to understand. What does arg mean, folks?
Argument, the minimum
Exact.
argument.
No. Minimum comes later. Arg is
Okay.
just arg. Correct?
Argument.
So what this means is the arguments of the function that minimizes the function. All right, that's what this arg min means. So here the argument is theta. So what this means is it is the theta values that minimizes this function. Don't you realize that there can also be an arg max? Not in this case, but I can also come up with an arg max, right? In which case that would mean the value of theta that maximizes that function. Okay. And whatever theta that is, we don't know what that theta is. It is some theta. Now that theta, I'm calling it as theta hat. So theta hat is that theta that minimizes this function. All right. So what we are on the lookout for is the theta hat, which minimizes the average cost function. Okay. Now, is theta a vector or a scalar?
Vector.
Vectors.
Vector.
Okay, fine. So let us say, so let's go back to this problem. Can you tell me how many scalar values are there in that vector? A vector comprises of scalars, right? So how many scalar values are there in that vector? In this particular context. Take this problem.
For W, it's 6. If we include B, it is 7.
We also include B, right? Because we're also going to estimate B, correct?
Yes, we see.
Right? So how many? So
7.
7, exactly. Why? Because I have a W1, I have a W2, W3, W4, W5, W6, and then a B, correct? So which means theta is a vector comprising of 7 scalars, okay? Next question. How many possible values of theta? Very poorly worded. Apologies. Are there? How many possible values of theta are there? Take this example.
Is equal
Take
to
this example. How many how many possible values of theta are there? Theta is a vector, but how many possible values are there?
1.
Think. Theta. I'm not talking of theta hat.
It depends on how we
Theta
train the model.
How
theta
many
can take
possible values?
infinitely many.
Exactly.
Yeah.
It can be infinitely many. Why? Because I can have any combination of W's and B's, isn't it? The possible values of theta is actually infinite, right? I can pick some combination of W1, W2, W3, W4, W5, W6, and B, and that's 1 theta for me. I can pick another combination, so on and so forth. All right. And what is M?
Number of instances.
Number of instances, number of data points, essentially. Number of, okay. In our world, since we are talking of documents, how many? This is the number of documents, correct? Would you agree? This is one document. Let's say there are many such documents. Then M in this context is the number of documents. Okay. So now the good news here is that this looks very daunting, isn't it? Infinite number of thetas. I got to figure out a way. Looks pretty daunting, isn't it? Right? Now, thankfully, for logistic regression, this loss function is a convex function. Why does that matter?
It converges at some point.
Exactly.
It can reach the
So,
global minimum.
so
Minimizes
yes,
it
exactly.
rapidly.
I think the better definition is you would have a global minimum. What do you mean by global minimum? Now that you're talking of a global minimum, is there another kind of minimum?
Is
Local
local
minimum.
minimum.
Local minimum. What is the difference between local minimum and a global minimum?
Local minimum is the minimum between some range. We are restricting into some range. Whereas global minimum is the function is over the
Okay,
entire space.
give me an analogy.
Okay. For example, for sine, if you are taking from
No.
0 to
Give me an analogy from geography. From geography.
okay. For example, there are two mountains,
Okay.
which for one mountain is shorter than the other. So the first mountain
we're
is
talking of
valley.
minima. We're talking of minima. So why mountains?
Sorry. We can take some valleys.
Okay.
We are traveling the first valley and we are reaching on minima, and that's local minimum. Whereas the overall journey, you would have reached some minimum point, and that's the global minimum.
So let's do something so that let's do something.
two,
So I'm going to delete this. So let's say this is the function. Okay. Now this is a minima. This is also a minima. I'm calling this minima 1, calling this minima 2. Now, which one is the local minima?
Minima 1.
Okay, this is the local one, correct? And which one is the global? This is the global.
Minima 2.
What does gradient descent do? Basically, you start at a point, some arbitrary point, and then start moving down that curve and reach this point. So for example, if I start here, what would gradient descent do? Come all the way down, reach here. Do you see what the problem can be?
So we can be logged in a local minima.
Exactly. So it is quite possible that you can get trapped in this well, right? That is possible. So, but a convex function doesn't have this problem. In a convex function, you will have something like this. So which means you will not get trapped in a local minima. Okay, so you can come all the way down without getting trapped in a local minima. You can reach the bottom of the valley. That's your convex function. Thankfully, logistic function is a convex function.
Is
Or,
it correct me if I'm wrong?
Mhm.
Only neural networks would have something as in the first thing, right? Local and global, or
Not
because
necessarily. Why? Don't you have functions like these in calculus? Something like this and like this in calculus? You can think of some function.
no. For cost functions of, I came across any other. I didn't come across any other functions which has local and global.
Pick a good calculus book. You'll see them. You can pick the. Okay, let me. I don't know whether I have it handy. Give me a moment. Look for. Give me. I'll just tell you what you need to look for. Okay. MIT calculus Strang. So there are 3 books here. Look for, I think, book 2 or book 3, one of those. They talk about this specific aspect. I faintly remember seeing a function where you have global minima and local minima. Okay.
And it's an optimization function.
Sorry, say that again.
And it's an optimization function, am I right? Because
it's a function. That's it. It can be some problem can result in that function. Correct. It depends on the nature of the problem. Okay. So you can check. There is a possibility. Otherwise, people. I mean, this is much before we started talking about deep learning and neural nets and stuff like that. Okay. So now coming back, we are lucky that we're going to deal with a convex function. So that does matter because it makes our life easy. Number 1. Question. What happens if we don't average over examples? So let us say there are, we'll go back to this again. Let's say there are m examples. Let's say I don't do this average. Then what happens to the cost function?
a way larger, because
Sorry?
a way larger than
Think. I'm not averaging. I have m examples, so which means I have 1, 2, 4, all the way
Okay.
up to m examples, correct? And I'm not averaging. So if you look at this expression, this is averaging it,
Keeps
correct?
oscillating.
Oscillating means you have to move from something to something else. What is this something to something else?
Yeah, when we move from one instance,
Alvin asked.
Question.
Okay.
Oscillating
Think
the
about it
cost.
this way. Are you if you're not averaging it, would you be dealing with one cost function?
No.
No.
Okay, so how many cost functions are you going to deal with?
M cost function.
Exactly. So you'll be dealing with m cost functions, correct? So you take each example and construct a cost function. It's like saying, look, this LCE, if you look at this, in bracket, there is an xi and a theta and a yi, correct? So what am I doing? I'm creating m such LCEs, right? And I have m such cost functions. So when you average it, the advantage is you're going to deal with one cost function, which is averaged over all your examples. But if you don't average it, then you're going to deal with m different cost functions. So make it very, very clear. Okay. Now, okay, of course, this is how do you go about plotting it? Let's not worry too much about it. I think you can understand that. Basic idea of gradient descent. Here's a simple example where there is just one W. We don't have W1, W3, W4, W5, so on and so forth. There is W and then there is loss. Okay, nothing else. Let's keep it very, very simple. And here is a nice convex function. So what is the objective? You take a point, you start at a point, you move to the next point. How do you move? Basically, forget eta. Eta is what is called as a learning rate. I'll come to what learning rate is. What is this? This is the first derivative of the loss function, okay, with respect to W. So basically the derivative will give you the slope. You basically move in the opposite direction of the slope. So so don't worry too much about opposite direction and all that. Essentially what you're doing is calculate the derivative and then you're going along that line, which is a slope. Now, how far do you go? That is determined by eta. Eta is a constant, all right? You can decide what eta is, by the way. So for example, if eta is too large, then you might end up coming here. Would you agree? If eta is too small, you'll probably lie somewhere here, okay? Now, in the world of machine learning, what is eta called? There's a very specific, no, learning rate is fine. There's another term for that. What is that?
Step size.
Another term. More, go one level above. Okay, question. What is the difference between, okay, so in machine learning parlance, or rather in machine learning vocabulary, what is the difference between this eta, the theta and eta? What is the difference between the two? Theta, of course, we know. This represents W1, W2, B. This, of course, is the learning rate. What is the difference between theta and eta? Why didn't I include eta in theta itself? Why I need this new fancy? I could have just included it as part of my W1, W2B, right? I could have just said, look, okay, I'm going to do this.
You couldn't read it as some hyperparameter, right?
Exactly.
It's something.
Exactly. The operative word is hyperparameter. Eta is what is called as a hyperparameter. Theta is a parameter. What is the difference? What is the difference between a parameter and a hyperparameter in the world of machine learning?
Actually, parameters are the which we could learn during the training and
Okay, what is hyperparameter?
help us to train the variables, the parameters.
Can you
We
give me a
should
better
make the
can you give me a better answer? Okay, let me put it this way. Okay, I'm a machine learning engineer. Would I supply thetas as an input to the algorithm, or are the thetas figured out by the algorithm?
Figured out by the algorithm.
Exactly. Let's come to eta, the learning rate. I'm a machine learning engineer. Is eta determined by the algorithm, or is that something that's supplied by the machine learning engineer?
Supplied by the machine learning.
Exactly, that's the difference. So eta is an input to the ML model. Theta is an output of the ML model. Reshma, can you go on mute, please? Thank you. Unless you're speaking. All right, thank you. So hyperparameter is an input to the machine learning model, and the parameters are outputs of a machine learning model. All right. So going back, when you do gradient descent, what are we doing here? You take the previous, you start with a weight. This is supplied by the machine learning engineer, the ML engineer. This again requires some, trial and error to figure out what eta will work well. And then this is, of course, the first derivative. Okay. Now, of course, the magnitude of the amount to move in gradient descent is the value of the slope weighted by this eta, a learning rate. Okay. So, of course, eta can be big, eta can be small, whatever, right? If eta is huge, you will move faster down that curve. If eta is small, your steps are going to be smaller, so it takes more steps for you to reach the bottom of this valley. Okay. Now, so let's do this. I want everyone to do this. So first thing we have to do is we have a logistic function, sigma z is equal to 1 by 1 plus e power minus z. That's our logistic function, correct? We understand that because that's where the whole story began, right? Sorry, not logistic function, the sigmoid function. Apologies. It's logistic regression, but this is a sigmoid function. So first step, folks, let's determine the derivative of this. So what is the derivative of this? Just come along with me.
E power minus z
Okay.
by 1 plus e power minus z.
Okay, 1 plus
A whole square.
Okay, how did you determine that?
U by v method.
Okay, alternatively, much simpler. Can we write this as e
1
power
plus
minus
e
z?
to the power of
1 plus
Power
minus
The
1.
whole power minus 1.
All right. So this would be minus 1 into 1 plus e power minus z the whole square multiplied by the derivative of minus z with respect to z, which is minus 1, correct? Right? Sorry.
Yeah, you're right.
Sorry. Apologies. Give me a moment. I'll have to do some change. Give me a moment. I'll have to calculate the derivative of this thing inside the bracket, which is nothing but e power
0 plus e
e power minus z, and then the derivative of
minus 1.
minus 1.
Minus z, which is minus 1.
Correct, exactly, minus 1, right? So that if you do all this computation, you get to this. Now this we can split it as, sorry, why is this struggling? Why am I struggling with this? Give me a moment, folks. Can I write this as 1 by 1 plus e power minus z into e power minus z divided by, can I write it this way? And this is nothing but sigma z into 1 minus sigma z. Would you agree, folks, on the call? I don't know what's wrong. Sorry, I'm unable to put that. Yeah, sorry. Any questions so far? So what we've done here is we just split this into two parts, 1 by 1 plus e power minus z into e power minus z divided by 1 plus e power minus z. This, of course, is 1 minus sigma z. This, of course, is sigma z. Okay. So the sigmoid function has a very interesting property that when you calculate the derivative of sigma z, it is nothing but sigma z into 1 minus sigma z. Okay, I'm just calling it not logistic. Let me change this to sigmoid so that there's no confusion. All right. Any questions so far? I hope this is clear. Okay, now, before we do all this, let's do something. Let's do this. So if I have sigma z is a function, z is equal to, let's say, w1 x1 plus x2 plus so on and so forth. Now, can somebody tell me if I have to calculate? Okay, let me put it differently. Let's go back to this function, folks. We have the cost function. Where is the cost function? All right, so here is the so if you look at this, this is the cost function. Sorry, let's yeah, let's use this. No? This is for one data point, correct? I can do a sigma and then divided by m for m data points. Okay. Now, so if you look at what I've done here is I basically determined for 1. Assuming this is the cost function and you don't have that sigma, we are trying to figure out the partial derivative of this function with respect to W1. Okay, question. If W is equal to W1 x1 plus W2, sorry, not W dot x equal to x2 plus W3 x3 plus, let's say, W6 x6. Now, can you tell me, and then there is a B as well, how many partial derivatives would you calculate? Because we're going to do gradient descent, right? So if you have to do gradient descent, how many partial
7.
derivatives would you calculate?
7.
That's right, correct. So you'll calculate 7 partial derivatives. So basically, dou this LCE by dou W1 all the way up to dou LCE by dou W6, and of course, finally, dou LCE by dou B. All right. So 7 partial derivatives. Okay. Now, so let's go back to this function here. Now, can somebody tell me what does Wj mean here?
Can vary from
But question, when they say Wj, is it right to put this in bold?
No, in that case, it's not a vector. It's a
It's
scalar.
scalar, right? But okay, you raise a very valid point. So let's see what the book does. Okay, these are very, you might think it's very minor, but let's see what the book does. Okay, I picked it up from the book. I'll tell you, even the book gets it wrong at times. Give me a moment. You see, here they got it right. But let me show you something, okay? Okay, this is Feb 23. I mean, they released this book only a few days back. I'm going to the Jan 2023 release, and I'll pick this book. Give me a moment. You see this, folks? They got it wrong here. You see that? They're denoting it as though it's a vector. So in some of the older versions of this book, the notations are incorrect. For somebody like a Stanford professor to get this wrong is odd, but the fact is I've seen some versions where it is wrong. Okay, so let's go to the book, the latest book. They got this right here. So let's not go to the presentation. Let's just focus on the book. Okay. Now can somebody tell me what does this mean? Partial derivative of LCE with respect to Wj. What does it mean? We are calculating the partial derivative of the cost function with respect to what?
Respect each weights.
Exactly. So we pick one weight, right? So when you say Wj, we are looking at one weight. J can be anything, isn't it? J in our world, J can take the value from 1 to 6, correct? Now, so you are calculating the partial derivative of this expression. So you can comfortably move this partial derivative into the function, which is what they have done here. No rocket science here. So far clear? I hope it is. Now let's look at this bit alone, folks. Just look at this. Can we take y out of the partial derivative? Can we take this y out of the partial derivative?
Yeah, it's a constant.
Constant. Why? Because we are calculating the partial derivative with respect to wj. So we can take y out of the partial derivative. Now, log of this expression. What is the so first step is you're calculating a derivative of a log. So what's that? What is derivative of log x?
1 by x.
1 by x. So don't you see? You take y out, and then this is your x, this whole thing. So that becomes 1 by this whole thing. You see that? Is it so clear so far? And then I need to calculate the partial derivative of this function that is there inside. Is that clear? So we've just applied the chain rule. One step of the chain rule to take y out. We calculated the derivative of the log, which is 1 by, log x is 1 by x. So this whole thing comes to the denominator. And then we stop here where we are yet to calculate the partial derivative of this function. Okay. And we do the same thing here. We take 1 minus y out, log of this whole thing. So which means this whole expression comes to the denominator, and dou by dou wj, this whole expression. Okay. Now, all that we're doing here is rearranging terms by taking this whole thing out of the bracket here. Okay. I hope this is easy to understand. So if you take this whole expression, because this is common here and here as well, out of the bracket, you get something like this. Okay. Now, let's come to forget what is there in the bracket. Let's just focus on this. What is the derivative of a sigmoid function? What is the derivative of a sigmoid function? So if the function
Sigmoid
is
into 1 minus sigmoid.
yeah, so exactly. So which means we just had a look a while back. So if you have a function sigma z and you're calculating the derivative, then the derivative is sigma z into 1 minus sigma z, correct? So don't you see, if I'm calculating the derivative of sigma of w dot x plus b, then it is sigma w dot x plus b into 1 minus sigma w dot x plus b, correct? Think of w dot x plus b as z. So that you're calculating, but then this is a partial derivative. So you'll have to apply the chain rule, which is partial derivative of w dot x plus b with respect to wj. All right. Now let's look at this, folks. Let's look at this alone. Partial derivative of w dot x plus b with respect to wj. So let's go back to partial derivative of w dot x plus b with respect to wj. So let's say we have w dot x is w1 x1 plus w2 x2 plus sum wj xj. All right. Now, can you tell me what is the partial derivative of this expression?
XJ.
Exactly, it's xj. Why? Because this is with respect to wj. So what is the partial derivative of this?
0.
0. This again 0.
0.
So the only thing that matters is this, correct? So when
Yes.
I'm calculating a derivative of this with respect to wj, I would get xj, correct? This is like saying if I have to calculate derivative of 5x with respect to x, then it is 5. It's something like that. Okay. So that's xj. So coming back, so this whole expression becomes xj. Now, what are we doing here? Let's understand this. No rocket science. Don't you see that this denominator here within the bracket and this, they cancel out, right? It is this and this cancels out. What is left is just this numerator and xj. That is all that is left. All right. So of course, there's a minus sign here. So they bring the minus side inside. So this is nothing but sigma w dot x plus b minus y multiplied by xj. Okay. So the partial derivative of this cost function with respect to wj. But of course, when we say this cost function, we're not averaging it out yet. Okay. We're just taking one data point, I mean one record, we calculated a cost function and we're calculating a partial derivative with respect to wj, and that is nothing but sigma w dot x plus b minus y times xj. Now, can you tell me, given our notation, what is this? This whole sigma
Y hat.
w y hat, exactly. So can't we say this is nothing but finally y hat minus y multiplied by xj. So that's the partial derivative of the function with respect to wj. All right. So if there are 6 such w's, then you would, it's y hat minus y times x1, y hat minus y times x2, so on and so forth. Okay. Now, food for thought, think and come back. What would be the, you can come back next class. This is, of course, partial derivative of this function with respect to wj. But what if this were to be replaced by b? How would you calculate that? Okay, think about it and come back in the next session. How would you calculate partial derivative of the cost function with respect to b, which is the bias? Okay. Any questions? I'll just stop here for questions. All right. If there aren't any, I'll stop for the day. What I'll do is I'll share the book in the channel. A lot of stuff there, but I think you should be able to relate to what has been done in the session. Strong recommendation, go through this derivation again so that you get a hang of how this is derived. Again, strong recommendation, derive it on your own using a pencil and paper. You'll understand a lot. All right. Thank you, folks. Catch you on Friday.
Good night, please.
Good night.